Hey everyone, Tim again. If you didn't get a chance, make sure to check out the first part to this video before watching. Did you watch it yet? Alright, awesome. In this video, we're going to talk a little bit more about musical instruments, particularly how they make sound. To recap really quickly, when you play a musical instrument, not just one sound wave is emitted, rather an entire series of discrete frequencies called harmonics. The set of all harmonics for a note is known as the Overtone Series. Wait, I know we learned all this in the last video, but why is it even true? Why does the Overtone Series even exist? Can we prove it exists? Let's see if we can figure out why the Overtone Series might exist, because that may help us understand the physics of it all. Then maybe we'll know how to prove its existence. In this video, I'm going to use a guitar as my example. Guitars, whether electric or acoustic, make sound when the strings vibrate. To make things easier, we're going to look at only one string on the guitar. Here's what happens if we play it. So, you might ask, how can we play different notes? Like we said before, thinner waves lead to a higher frequency, which mean higher notes. So, to make the note higher, we just need to make the vibrating part of the string smaller. Easy. We can do that by pushing our finger down on the string to restrict the vibrations to a smaller section of the string. Now the note sounds like... Cool, so that's how we change the note we're playing. That still doesn't explain the Overtone Series. Well, to think about the Overtone Series, we have to think about which waves can even be played on a string. Because the string has two fixed ends, those parts can't vibrate. They're stuck in place. So, the rest of the string has to oscillate instead. We call the waves that can oscillate on a string with two fixed ends standing waves. If the only rule is that the ends of the string are fixed, it sounds like we can form a lot of different standing waves. What's the easiest one we can make? Okay, let's have the whole string vibrate, kind of like a jump rope, and have the two ends stay fixed. What does that sound like? Alright, what would the next simplest standing wave look like? Instead of one bump, let's make a wave with two bumps, like this. What does that sound like? Okay, if we keep making more of these, adding a bump each time, we get this, and then this, and so on. That series goes on forever. Now, to see which of those overtones are played, I looked up the frequency analysis of a guitar string. This graph shows us which frequencies are most observed in a recording of a guitar string. We can see spikes at each of the overtones, the largest one being the fundamental frequency, or the simplest overtone we made. So, we should expect to see mostly that wave if we look at a guitar string vibrating. Well, I wanted to find that out, so I googled guitar strings vibrating. I found a video uploaded by YouTuber Nico Getz. He put his camera inside his guitar while he was playing the strings, and this is what it looked like. That's not what I would have expected. Since we're looking through the hole in the body, we should expect to see a subsection of the simplest wave on each string. Kinda like this. To help figure out what's really going on here, I went down to MIT's Strobe Lab, a center for research in high-speed and scientific imaging. I got the chance to meet with Christian, a senior at MIT with a lot of experience in high-speed photography, and I asked him about my problem. Yeah, it's weird. This is not what I expected at all, actually. What do you think's going on?
So this, I'm thinking, it looks like rolling shutter.
Rolling shutter? What's that?
Right, so nowadays digital cameras have image sensors, just effectively arrays of pixels. Right, the sensor, what it does is scan each line one at a time. And so for one frame, what you've really got is the addition of what the sensor scans here, then here, then here, then here, then here, then here. So one frame doesn't really represent one instant in time. One line represents one instant in time. One frame is the sum of those. You see this if you take pictures of guitar strings or anything really that sort of oscillates or vibrates quickly. Take, jet turbines, just spinning wheels, a wheel that spins quickly enough, you'll get rolling shutter effect.
Oh, okay, that's really interesting.
Yeah.
How do you think we should avoid that?
Let's go high speed.
So, we set up a high-speed camera and got to work. Ah, so that's what it's supposed to look like. You can really make out the fundamental frequency. What about the other notes in the Harmonics series? You can actually force the guitar to play those waves instead of the fundamental frequency. That is, if you lightly touch the string halfway down, it will block the fundamental frequency, and it will only allow the next overtone to play. Doing this prevents the fundamental frequency from playing a sound because the wave is not stationary at that point. With our finger there, the string can't be vibrating. So, we end up hearing the note with double the frequency, or 1 octave above. Well, we learned the physics and we found our proof, so it looks like we're done. Thanks for watching.